Okay, so this previous topic of going through carbocation stability, this all had a purpose to help us try to explain the final result of this more complicated alkene reaction, which we presented up here. So this was a slightly more complicated example than, ethene reacting with a hydrogen halide. We said that the result was that you could get either product B or C, that these resulted from two different intermediates, D and E, which then themselves resulted from this starting material A, which is the same thing as up here, and A reacted with HCl, and these two arrow pushes could result in either D or E, because inherently the flaw with this arrow pushing mechanistic design is that you're not really, there's no inherent designation about which carbon gets that red H. So because of that, we have to explore both. So we then said that carbocations, these could be linked or ranked by stability depending on their structure. And from there now, what we're going to do is we're going to try to answer a very important question. So a question that we'll answer or try to answer over and over again is this kind of major / minor question, or major minor product question. So which one is the major and which one is the minor? Is B the major product that will result, or will C be the major product that results? This actually has very big implications, because if you wanted to make one product over the other, it's very useful to know, well, should I even try to make this molecule this way, or should there be an alternative way of doing it? So let's try to answer the question, which product is the major product and which product is the minor product? Will B be major or will C be major? So the way we're going to try to rationalize this out is with an energy diagram. So an energy diagram is going to, this should look relatively familiar from intro chem, so you've probably seen these before. I'm going to kind of go down a tiny little bit. So on the y-axis is free energy, and I'm just going to indicate that with an E. So this is just energy on the y-axis. And the higher you are on the y-axis, the higher the energy. The lower you are on the y-axis, the lower your energy is. And so what we're going to be doing as we go from left to right on the x-axis is we're going to be talking about reaction progress. So reaction progress. So what this then says is that on the very far left of the reaction, this is the very beginning of where we're going to be. And the very far right is going to be at the very end of the novel, at the very end of the reaction. These are the products that we're going to get. And we can actually try to quantify the energy of all of these molecules. So we can do a pretty good job of guesstimating, the energy of A, B, C, D, and E. And so this is actually going to give us a lot of information about which product or which final product is going to result. So let's start with the broad strokes overall. So we can fill in A, so this is the starting material. And let's just give A a relative position on the y-axis of maybe right here. So this is A. So we're going to start off with A. That part's checked off. So we checked off A on the y-axis. And so we can actually check off relatively easily B and C as well. So B and C, both of these are alkanes, and they do have slightly different structures. But the important point to note is that really at the end of the day, these slight differences in structures really aren't going to make too big of a difference in terms of that location on the y-axis. So for all intents and purposes, let's just say that B and C both have maybe a location maybe right here and right here. So I'm just kind of offsetting them a little bit, but let's just say that B and C are over here. And overall, B and C will have, slightly lower energy than A, okay? So what we're going to now do is try to talk about D and E. So the differences in D and E are going to be, way different than the energy differences between A and B and C. The main reason for this is that A, B, and C are neutral. D and E are charged. And in general, the general rule of thumb is that if you have to compare a charged species to a neutral species are going to be way more stable than charged, okay? So the way that we can relate this to our y-axis is that more stable species are going to be lower in energy, and less stable species are higher in energy. So what we can say then is, again, more stable species equals lower energy, or lower on the y-axis, and less stable species are going to be higher on the x-axis, or higher on the y-axis, or they're also going to have a higher energy, or higher E. So now that we've checked off A, B, and C, let's try to check off D and E. So we already know that both D and E are way higher on the y-axis, just by default, when compared to A, B, and C, because they are charged, and A, B, and C are neutral. So overall, D and E should both be way higher on the y-axis, but now what we can do is we can compare and contrast that relative location between D and E. So if we look at D, D is primary and E is tertiary. And we also talked about, just a lecture ago, of how we can talk about relative stability between primary and tertiary carbocations. And so try to remember which one's more stable. Pause the video. Hopefully, after you paused, you thought about it for a second and you saw that the tertiaries were more stable than the primaries. So tertiary carbocations more stable, and so then they should be, which way? Should they be higher or lower than the primaries on the y-axis? And yes, they should be lower on the y-axis than the primaries. So then what we can do now is, since we know that E is actually going to be lower on the y-axis, so this is going to be lower, this is going to be higher. So now we've filled in our energy diagram.